Okay, next up we have Max Newman from Rutgers University. Talking, the title of the talk will be Towards a Robust Tip of the Red Giant Branch Calibration in the Era of Roman.
How's this? Can you hear me? Great. All right. So hi. For the next 12 minutes, I'm going to first emphasize the importance and fundamentality of measuring distances to galaxies. I'm then going to introduce the tip of the red giant branch method. I'm then going to talk about the empirical approach we take to calibrating the tip of the red giant branch method in the near infrared and HST, in Hubble and JWST. And then I'll move on to Roman and talk about the prospects and what I see as being the strengths for Roman in terms of the TRGB method. Cool. Most, if not all of us, in some aspect require distance measurements to galaxies or objects. And to highlight the importance of them, I just have 3 galaxies. Without the distances, we can say that they're spiral galaxies. We can say that they look a little bit different. But without distances, we don't have a way to quantify differences in mass, star formation rate, and in myriad other galaxy properties on absolute scales. Absolute scales being the important term here. In addition, without galaxies, without distances to galaxies, we wouldn't be able to make this type of map, which shows the nearest superclusters to our galaxies. So without these distances, we wouldn't be able to see this magnificent structure. How we measure distances, though, the methods we use to measure distances is highly scale dependent. And so we can look at this figure here, which shows from the left to the right, increasing distance from the Milky Way. The top shows the scale is in both redshift and megaparsecs. At distances in redshift greater than about 0.1, redshift-based distances can be a reliable method or are a reliable method to get distances to galaxies. But within a redshift of 0.1 being pretty conservative estimate, we need different methods to get robust and precise distances. Among these, we have resolved star-based methods such as the tip of the red giant branch, as I'll be talking about. Cepheid variable stars are earlier, and there's a number of other methods, including geometric-based methods listed at the bottom of this figure. As I said, I'll be focusing mostly on the TRGB, or just on the TRGB today. And as an example of how the TRGB has been applied and has been a major tool, we can look at the cosmological distance ladder. We start by measuring or calibrating the absolute brightness of the tip of the red giant branch using geometric methods in the Large Magellanic Cloud and the Megamaser NGC 4258. Then we use the tip of the red giant branch to measure distances to nearby galaxies that host type 1a supernovae in order to get a handle on the absolute brightness of the type 1a supernovae. And then finally, we can measure the distance to type 1a supernovae out in the Hubble flow. And this is just one major application of the TRGB. There are other ways, you can use other methods, but in particular, the TRGB has been a very major component of this analysis, and especially in recent years. But what is the TRGB? So the TRGB is a feature observed in a color magnitude diagram. There are 2 color magnitude diagrams here. So magnitude on the y-axis, color on the x-axis. It appears as a sharp cutoff in the number of stars at the tip of the red giant branch, so TRGB. And in theory, the TRGB stars are all the same brightness. But in practice, we observe stars in different bandpasses, and the TRGB brightness is dependent on the bandpass that we observe it in. So on the left-hand side, I'm showing a synthetic population of stars, specifically the red giant branch. It's a very narrow red giant branch in this case. These are as if they were observed in the Hubble Space Telescope F814W filter. And then in the inset, I've highlighted with an arrow the location of the TRGB, and you can see this nice cutoff at the top of the red giant branch. Similarly, we can look at the middle panel, which shows the TRGB, but now in the JWST F90W filter. When we move to the near infrared, however, which is shown in the right panel with the JWST F200 filter, F200W filter, the TRGB is significantly brighter, and I've added this dotted line that's set to the level of the TRGB magnitude in F814W, just to really highlight how much brighter the TRGB appears in the near infrared. But I also want you to notice that the TRGB as a function of color, the TRGB brightness as a function of color changes as you go from bluer to rather, or from like, you know, if we take 606 minus 814 in the left panel, so we go from left to right, the TRGB is flat, and that's indicated in the insets. It's very similar in F90W in the middle, but when we go to the right, there's now this significant dependence on the color, significant dependence for the brightness of the TRGB on its color, and so you can see it's linearly increasing. This effect is one that's due to metallicity and age differences, and the color traces these metallicity and age differences. So in order for the TRGB to be a robust and precise distance indicator in the near infrared, we need a way to calibrate this metallicity slash color dependence. So we just did that. We did just that. We had a JWST or an HST program as a preparatory program for JWST. We imaged 4 galaxies, 2 fields per galaxy. And each set of observations had overlapping F814W HST, which already has a well-known TRGB calibration, as well as near-infrared data. We first anchor our distance scale. On the left over here is a galaxy image of NGC 253, which is one of the galaxies in our sample. And it's just represented, this observing program is representative of the rest of our program. On the right here, I'm showing a color magnitude diagram of the ACS field, which is shown as in the green footprint on the left image. This is representative of our data, and this is a TRGB measurement for NGC 253. We do this for each field in each galaxy in order to set up a uniform distance scale. We then use that uniform distance scale we've set up, and we go now to the near-infrared data, specifically F110W and F160W on HST. And in order to maximize our color baseline, in order to characterize the slope of the TRGB or the color dependence of the TRGB, we convert all of our data, these are all of our data, to absolute magnitudes, take every single one of our fields and stack them together. And so this is what that looks like on the left side over here with F160W on the y-axis. I've also highlighted the slope that we measure. You can see it with the arrow and also with the black line with the red shaded region. After measuring the slope, we can then remove the color dependence such that all stars at the TRGB are now at the same magnitude. And then we measure the 0 point, and this is our characterization of the tip of the red giant branch in the near infrared. Great. So now we've developed this method with HST, and we have a way to do this in JWST. And we did just that. So on the left here, I am showing, before I get into that, our JWST program was designed to image one of the 2 fields from our HST program in NearCam. The CMDs I'm showing here are from all of our data. 77, the slope is -1. There is a significant color dependence. And again, we can go through the same process.
Recording in progress.
Okay. So we didn't just do this for these two sets of filters. We actually did this for 6 different filters, and I think it was about 18 different combinations. And we have a paper out about this. It's in a review process right now, but there'll be QR codes at the end of the talk. We're also going to be doing this with NIRIS, F90W, 115W, and 150W, so stay tuned. So now, what we're all here for, Roman. I had to make this the title. I just couldn't help myself. Roman, in my eyes, is going to be an incredibly powerful tool for TRGB work. the field of view of a single Roman WFI exposure gives us access we have not had before to investigating the spatial components of the TRGB in one shot, or stellar populations in one shot. And so in particular, when we try to calibrate the TRGB in Roman filters, and if we have observations of a single galaxy, we can be picky about the fields that we use. We can choose the fields with the lowest crowding and create the highest fidelity photometry catalogs. We can test the metallicity dependence of the TRGB across the entire galaxy. And importantly, we can build the number statistics of the TRGB stars so that we have a robust data set with which to work. I'm going to try to give a representation of how I think the Roman WFI observations of a single galaxy would allow us to work with and examine different fields. It's a very crude approximation, so I've just simulated, I think I have 6 different examples that I'll go through quickly. So on the left-hand side, on the y-axis is always going to be Roman's F087 filter, and then the color axis is F087 minus F158. So here we have a CMD that shows significant non-RGB contamination, and I think, let's see if I can, So when I say non-RGB contamination, I mean red helium burning stars, AGB stars that sit next to or right above the TRGB, which is right here. I'll wrap up soon. Here we have another CMD, which again shows these significant non-RGB populations, and we also have lower TRGB star counts. Again, here's something with CMD with modest contamination and low number statistics at the TRGB. Here we have minimal non-RGB contamination and a wide metallicity range. Here we have a red giant branch with almost no contamination at all. And here is a field that we would not use for TRGB work, where you cannot even identify the TRGB. But we have the flexibility, if we can observe the whole galaxy in one shot, to be able to make these types of observations and decisions. And so to wrap up, how does the TRGB with Roman advance science? Well, we can use Roman to measure H0. That's a really big point of this. We will be, hopefully, and I expect many dwarf galaxies in the field to be discovered. And so with Roman, we can measure the TRGB distances to these galaxies readily. And there are still a plethora of spiral and early type galaxies that do not have secure distances that we will be able to do this with Roman. So I'm going to leave these QR codes. The left-hand side is the HST calibration, and the right-hand side is the JWST calibration paper. I'm happy to take questions, and I've also posted my email here just in case you can't think of one right now. So thank you.
Thank you very much. Any questions? I see in the back there.
Thanks for the excellent talk. Regarding the dwarf galaxy science case, how do you deal with the fact that, like, nearly by definition, dwarf galaxies will have lower number densities, so the red giant branch will be more poorly sampled?
Sure.
Like, have you done forecasts to see if the density will actually be good enough to find the T in the RGB?
So thank you for the question. This is something that has continuously, or continues to be a topic of conversation. I have not done forecasting, but it is definitely something I want to do, and actually being at this conference has been really eye-opening to the tools that are available or becoming available to do these types of analyses, so I'm really excited about that. But yes, in order to measure the TRGB, right, like I've emphasized, you need the statistics to be able to identify the TRGB. And so there is going to be a scale or dwarf galaxies where it's just not possible, because you can't add stars to a galaxy that don't exist. So yes. But hopefully we can start to quantify how that's going to affect how many galaxies we can get precise distances to.
Great, thank you.
Sure.
Where does the overall 0-point calibration come from? Is it?
So in the case of our calibrations, so we first, internally we've tied it to the TRGB as measured in the HST F814W, which is tied to like geometric calibrators. So it's tied to the LMC. The 0 point for that is tied to the LMC, NGC 4258, the SMC, and then there is some contribution from globular clusters in the Milky Way.
Okay.
Yeah,
Thanks.
but I think that will improve. There are programs currently active to directly tie JWST to Gaia data.
Well, can you identify TRGB stars well enough to
That's what
parallaxes of stars that you know are TRGB, or it's that you'll find star clusters where you could identify
I
a
believe it's
TRGB?
more the latter, and it's kind of a TBD. We'll see. Yes, they're very bright. They're very hard. They're very hard to do. They probably saturate most of them, but I know there are a couple active programs at the moment that are going to try it. I can go look it up. We can have a conversation about.
Okay.
Yeah.
Thanks.
Any other questions? Yes, okay.
Thank you. Thank you for the talk. So yeah, David actually asked a bunch of the questions that I was thinking about, and I'd love to get into some of the details. But to further inform some of your studies, especially nearby, would you think about perhaps either including ground-based data, so increasing your baseline, right, to really truly understand that? So I'm thinking about LSST. And then also, would you also perhaps consider, I don't know, spectroscopic data, looking at that metallicity dependence? Do you kind of see where I'm going with that?
Yeah, so I see that definitely we've started preliminary discussions, but definitely talked about LSST with the TRGB to get those data involved. The idea of using spectroscopic data has jumped in and out of the back of my mind several times. At this point, I don't have a good sense of how I would incorporate it, but I would love to learn, try to go down that path and see how it could actually help with that metallicity, to directly connect to color and the metallicities. Yeah.
Okay, thank you very much. Let's please thank the speaker again.